But today we're going to get started with double integrals. And so in terms of my handout, just a quick refresher on all those integration rules. Because just like we were taking derivatives, and the whole idea behind a partial derivative is we're kind of thinking about one of those variables being fixed and taking the derivative with respect to everything else. When we're talking about double integration, we're doing the same thing. So we're sort of addressing one variable at a time. But it does mean that we've got to integrate some things. So this is just my refresher, basic power rule. If I'm integrating a constant, I have to pay attention to what variable that integral is with respect to, so that when I integrate that constant, I pop out a variable that matches what I'm integrating with respect to. Anytime I have something of the form e to the ax, that integral is 1 over a e to the ax. This isn't really worth writing out a u sub for. We really just want to think about it with that rule with the constant already in there. Refreshing our memory about natural logs, and a little bit of integration by parts and u sub might pop up in here. But I really just want to get started with some double integrals. And I'm going to start with just some examples of practicing it, and then we'll talk about like what the picture would look like to go with it for some context. So my first one on here, going 0 to 1, 0 to 1, 6 minus x minus 2xy dx dy. Okay, so the first thing that I want to sort of focus in on is the notation. And it's a double integral, so I've got two integration symbols. But what's important is that they're nested. And what that means is that these limits of integration go with the inside variable. So this 0 is actually an x equals 0, and this 1 is an x equals 1. And then my outside integrals match up. So that 0 to 1 matches up with the dy. So that outside 0 and 1 are telling me that y goes from 0 to 1. And mechanically, when we work through a double integral, we start on the inside first. So my first step is going to look at this entire piece and integrate with respect to x, which means anytime I've got a y in there, we're treating y as if it's a constant. So when I integrate 6, my variable that I'm working with is x, so that becomes 6x. When I integrate negative x, I'll get negative x squared over 2, or 1/2 x squared, depending on how you like it. When I integrate negative 2xy, I'm going to get a negative x squared y. So that's me finding the antiderivative with respect to x. I don't need a plus c because I have bounds on that integral. I have limits of integration. So those first set of integration limits say I'm replacing x with these values. This is still all nested inside of that other integral where y is going from 0 to 1. So I'm kind of computing that entire inside integral first. So if I plug in 1, I've got 6 minus 1 squared over 2, so 1/2, minus 1 squared times y. When I plug in 0, I will have 0 minus 0 minus 0. So conveniently, I don't have to worry about the zeros this time around. Again, that's all living inside of this integral from 0 to 1. You could worry about getting a common denominator and putting these together. I probably wouldn't worry about it at this step because they're both just constants, so taking that integral isn't so bad. So this time my variable of interest here is y, which means when I integrate a constant, I end up with 6y minus 1/2 y minus y squared over 2. And then this is going 0 to 1. When I plug in 1, I'll have 6 minus 1/2 minus another 1/2. When I plug in 0, everything is going to 0, so I'm going to skip that part. So I'm looking at 6 minus 1 or 5 for a final answer. So with respect to y, 4 is just a constant. So I'm going to get 4y. X is also a constant. So I'm going to get 4 minus x squared times y as well. I'm going to, no, I'll just wait. I was going to do something clever, but I'll wait on my cleverness for the next step. So if I integrate negative y squared, what should I get? Perfect. And now I'm plugging in y equals 0 and y equals the square root of 4 minus x squared. Questions about this step in terms of the antiderivative piece? We're good to plug in things. Okay. So I'm going to plug in that 4 minus the square root of 4 minus x squared. But this is the piece where I'm going to do something clever. This part, I can look at as y times 4 minus x squared. And the reason I'm going to do that is then when I plug in my y value of the square root of 4 minus x squared times another 4 minus x squared, I can change both of these to be 4 minus x squared raised to a power, which I think is going to be helpful. So this one, right, I've got 4 minus x squared to the 1/2 times 4 minus x squared. Well, I can write that as 4 minus x squared to the 3/2.
Oh, never mind. Yeah.
Yeah. So I can write that as 4 minus x squared to the 3/2 minus 1/3 of 4 minus x squared also to the 3/2. If I'm integrating first with respect to y, that means that 3x squared is just 3x squared y. Integrating this piece with respect to y, I've got x y to the 4th over 4 and y squared over 2. And then we're plugging in, we're replacing y with x squared and subtracting off replacing y with x. Sorry, other way around. We're replacing y with x and subtracting off replacing y with x squared. So if I replace all of my y's with x's, this becomes 3x to the 3rd minus, replacing my y with x's here, that's a total of x to the 5th over 4. Replacing my y with x here is an x squared over 2. And then all of that I'm subtracting off. X squared times x squared makes that 3x to the 4th. When I plug in x squared here, x squared to the 4th gives me x to the 8th times another x. So I've got x to the 9th over 4. Plugging in x squared here, I've got x to the 4th over 2. Now, since I already have things that have common denominators, you could choose to put those together, but I actually think that it makes it worse to deal with the fractions. I think we're better off just leaving all 6 of these pieces and integrating each of them with respect to x. So now I'm just quickly integrating with respect to x, add 1 to the exponent. It's going to give me 3x to the 4th over 4, x to the 6th over 24, x cubed over 6. And then I'm going to have negative 3x to the 5th over 5. Minus a minus will make that plus x to the 10th over 40. Distributing that minus sign through, I'll have x to the 5th over 10. We're going 0 to 1. Since everything has an x in it, when you plug in 0, you'll just get 0. So I really just have to plug in the ones. 3/4 minus 1/24 plus 1/6 minus 3/5 plus 1/40 minus 1/10. Don't mess with it. Just leave it like this. And if this were a web work problem, just type that whole thing in. Don't waste time plugging into a calculator. Certainly don't waste time trying to get a common denominator. Just throw it in there like that. And you don't have to actually compute it, but set up an integral to find this area. Do we remember how to do that from last quarter?
That line, y equals the integral y equals 8 minus the integral y equals x.
Okay, we can do it like that. So 8 minus x cubed. And I would be integrating that with respect to. And we would go from. So I'm going to turn that into a 19C problem. Here's the way I'm going to turn it into a 19C problem. This implied that we had some sort of arbitrary cross-section. I'm not going to make us do a Riemann sum, I promise. Some sort of arbitrary cross-section that was like vertical. So this represents essentially a top minus a bottom function. But if I rewrite this, that bottom function was y equals x cubed. That top function is y equals 8. And as a double integral, I'm integrating with respect to y and then with respect to x. That is a 1. So if I integrate 1 with respect to y, I would just get y. And then I would be plugging in an 8 minus an x cubed. And then I would be right back to the original integral that we had. So graphically, what this actually means and what we're really doing in a 3-dimensional space is when I have a double integral, and sometimes we write this just with a dA to mean either dy dx or dx dy, but like we're not specifying which. And sometimes we write an r over here to mean the region. And we put a function inside here. This is calculating a volume. With the 3D height, as z equals f of x and y. And the reason that it works like this for finding the area is, okay, I'm just gonna pretend. So my phone, I'm gonna pretend that it's 1 centimeter high. Like that's the overall thickness with my phone case. So that means that if I did the calculation to find the area of this thing, right, I'm just gonna estimate, let's say that's about 12 centimeters by 6 centimeters. So if I was calculating the area, I would have 6 by 12 and get 72 square centimeters. But if I now multiply that by 1 centimeter, the volume and the area have the same value, they just have different units. And so I can write a double integral to find an area if I just set my height function to 1. And if my height function is anything other than 1, I'm not calculating an area anymore, I'm really calculating some sort of volume. Octant, if I smash that flat and I'm just thinking about the x and y axis, means we're only looking at positive values of x and y. So if I am bound by x equals 2 and y equals 3, then I'm integrating over this rectangle. I have the choice whether to set this up with dy on the inside or dx on the inside. So if I set this up with dy on the inside, then, now let me do it. Yeah, if I set this up with dy on the inside, then this has to be y equals 0 for the bottom, y equals 3 for the top. And then for my outer integral, if that's dx, then my left-hand side is x equals 0, and my right-hand side is x equals 2. But I had the choice to set it up in the opposite order and set that up as a dx dy, where my x's on the inside went from 0 to 2, and on the outside, my y's go from 0 to 3. We should get the same answer. Yeah. So pick one of the two and finish it off just for some extra. So if I integrate with respect to x, then that first one is going to become 9x minus xy squared. And now I'm going to plug in 2, subtract off, plugging in 0. And just, I like to put the letter there to remind myself I'm plugging this in for x, not for y. So if I plug in 2 for x, 9 times 2, I get 18 minus 2y squared. When I plug in 0, everything's going to go to 0, so I'm not going to worry about that part. And now I'm integrating y from 0 to 3. So when I integrate 18, I'm going to get 18y. And this will be minus 2y cubed over 3 from 0 to 3. So 18 times 3 should be 54. And 3 cubed is 27 all over 3. So a couple of different options here, but 27 divided by 3 is 9. So 2 times 9 gives me 18. That's 54 minus 18, which I think should put us back to 36. We have choices, but when I look at this region, I either, if I'm going to take vertical cross sections, I have to break this up into 2 separate integrals. Because on the left-hand side of 0, where the x values are negative, I have this line as my top. But over here, I have this line with a negative slope as my top. So if I'm going to write this with vertical cross sections, then I'm gonna end up having to break this apart into two separate integrals, which is totally fine. Alternately, I can instead switch this to be horizontal cross sections. And then I can write it as one integral. Because everywhere in the region, I have the same, I have this line with a negative slope as my right-hand side and this line with a positive slope as my left-hand side. So what's your preference? Vertical cross sections and break it into two pieces? Yeah, okay, let's go vertical cross sections and break it into two pieces. So if I just kind of start getting that set up, then over here, that piece, I know that my inside limits are gonna go from y equals 0 to y equals, I'm just gonna call this line P for positive. What are my x bounds gonna be for this part? So I'm gonna go -1 to 0, and then we'll have e to the x plus y, and this is gonna be dy dx. For the second piece over here, I'm gonna call this line N for negative slope. Here, I'm gonna go again from y equals 0. We're gonna be adding these two things together, by the way. And this is gonna go until I hit line N. Same inner function that e to the x plus y, but dy dx. And this one, I'm gonna have x bounds going from 0 to 1. Now I have to come up with the equations of those two lines. Great news. I do not have to do a linear regression. It's 2 points. It's literally just like old school. Find the equation of the line. I didn't make it that much work for us. So if I need to find the equation of this line, for any line, I need a point and a slope. So for the line with the positive slope, I'm going to get that slope by doing y2 minus y1 over x2 minus x1. And I'm going to get a slope of 1. I've already got the y-intercept, so I know that that positive slope line is going to look like y equals 1 times x plus 1, or just x plus 1. On my negative slope side, if I find that slope, I'm going to do y2 minus y1 over x2 minus x1. And I'm going to get a slope of -1. Since they have the same y-intercept, I know this equation is going to look like -1 times x plus 1, or 1 minus x. I did a horizontal instead. I know it's not showing up super well, but if I did horizontal, then everywhere inside of the region, I have the same function touching the right-hand side. Like no matter where I am in the region, those cross sections always have that line with a negative slope on the right and the line with a positive slope on the left.
So the bounds be 1 minus x and x minus 1.
Well, if I switch to horizontal cross sections, then I have to rearrange the two equations. So this equation with the negative slope, if I rearrange to solve for, to make it say x equals, this side would be x equals 1 minus y. And this side would be x equals y minus 1.
And then you integrate those.
Right? And so if we did it this way, My outer limits would be the y values at the bottom and the top, and my inside limits would go, I'd have my left-hand side at the bottom, my right-hand side at the top, e to the x plus y, dx, dy. E to the x plus y, it's totally fine to leave it like that. I think when I'm doing either partial derivatives or partial integrals, when I'm doing double integrals, I sometimes prefer to think about that as e to the x times e to the y. Don't have to, but it's my preference. And part of the reason that I like doing it that way is if it helps you to sort of declutter what you're looking at, because it's being multiplied, you can now take the part that doesn't have y's in it and move it in front of the integral if you wish. Because that e to the x is a constant with respect to y. So I can treat this as e to the x times the integral from 0 to x plus 1 of e to the y dy, all of that nested inside of my dx. So if I integrate with respect to y, the integral of e to the y is e to the y. So I'm going to have that e to the x sitting out in front times e to the y going from 0 to x plus 1. When I plug in x plus 1, I'll have e to the x times e to the x plus 1 minus e to the 0. Yes, thank you. Thank you. Cool. Yes, that is a 1. And actually, I'll leave that as e to the 0. But I needed to distribute that e to the x, and I totally missed distributing that e to the x. Does that look better? Cool.
Then how did you get you the just when you have stuff?
So when I multiply, so I'm multiplying two things with the same base, which means I'm going to add the exponents. So I've got x plus 1. Yeah. Great. Now I'll plug in 0 and -1. So when I plug in 0, I have 1/2 e to the 1 minus e to the 0, which is 1, minus 1/2 e to the -1 minus e to the -1. Cannot be integrated the way it is written, or was just going to be really, really ugly. And when that happens, one of the tools that we have for double integrals anyway, is to try switching the order of integration. So if I look at this, and I was going to try to integrate this with respect to x right now, integrating the square root of x cubed plus 1, there's no u substitution I can do. It's possible that there's an integration by parts that might help me. I think I might have to use some sort of trig identity and do a trig substitution. Like, it's not friendly. Luckily, we've been given the hint to switch the order of integration. Now, I'm going to do it the wrong way first. You might think that we can just switch the order of integration. There's a problem with this. Negative sign is not the problem. There's a problem with this because this thing we can think of as representing some sort of volume. And the very last step we're gonna have on this one, after I've taken the antiderivative with respect to X and after I've taken the antiderivative with respect to Y, I'm gonna plug in 1 and 0. Whatever happens, I'm gonna get a number out of this integral. I'm not gonna get a number out of this. Because if all I do is literally flip the order of integration, the last thing I'm gonna be plugging in is a square root of Y. My answer was gonna have Y's in it. So this doesn't work. And instead, in order to switch the order of integration, we actually have to go back to what the picture looks like and rewrite it with our cross sections the other direction. So I'm going to start by constructing the picture. And my picture has to start by drawing all 4 of these bounds and reminding myself this was y equals 0, y equals 1, x equals 1, and x equals the square root of y. So if x equals the square root of y, that means y was equal to x squared. But this only takes into account positive y values, or rather it only would spit out positive y values. So y equals x squared would be an entire parabola. But if x equals the square root of y, a square root can never spit out a negative value. So that means I wouldn't have any negative x values. And then I have x equals 1. I have y equals 0 and y equals 1. So in terms of the region in question, sometimes, like in this case, there's kind of 2 parts to my picture. To figure out which part we're looking at, I'm going to put my pen on the inside lower bound, like whatever that graph is. So I'm going to start here on the curve that's the inside lower bound, and I'm going to move in a straight line to get to x equals 1, which means right now I have a horizontal cross section. And I have to flip that. So if I'm going to flip that, it means I'm going to end up with a vertical cross section. And that vertical cross section, my inside bounds, the function at the bottom is y equals 0. And the function at the top is y equals x squared. I would take those vertical cross sections as far to the left as x equals 0 and as far to the right as x equals 1. When we switch that order of integration, we haven't done anything to change that interior like height function. The only thing we're doing is changing the bounds. And then we're ready to integrate. This one, I will give you a chance to integrate on your own. After we switch the order of integration, is with respect to y, that whole thing is a constant. So when I find the antiderivative, it's just going to be y times that whole thing. And now I'm plugging in 0 for y and x squared for y. When I plug in x squared, I end up with something where I'm going to have the u substitution waiting for me. When you plug in 0, 0 times something, it's gone, so I don't have to worry about that part. Yeah, sorry. So now the u substitution is sitting there waiting for me. And if I let u equal x cubed plus 1, then my du is 3x squared dx. And I've got the x squared and I've got the dx. So I just need that 1/3 du is equal to x squared dx. I'm going to go ahead and switch my limits to be in terms of u as well. So if I switch my limits, when x equals 0, u is equal to 1. And when x is equal to 1, u is equal to 2. And that's going to let me switch my limits to say I'm actually integrating from 1 to 2 of 1/3 u to the 1/2 du. So all of those fun integration techniques from 19B and all of those integration skills we had last quarter, they're coming back around. We're going to need them right now, and we're going to need them when we dive into chapter 14, which is going to happen on Friday. So here, adding 1 to that exponent, I'll have u to the 3/2.
Okay, why is it equal to units? With these,
So when I plug in 1 for x, I'm going to have 1 cubed plus 1. Yeah. So I'll have u to the 3/2. I'm dividing by 3/2 or multiplying by 2/3, which means I think I'm going to have a 2/9. And now I'm going from 1 to 2. So I've got 2/9 of 2 to the 3/2 minus 2/9 of 1 to the 3/2. So let's pause for a second and look at this and say, why might I want to switch the order of integration? Well, the way it's written right now, to compute the dy part, I'm going to have to do integration by parts twice. Maybe that's the route we want to take. Or maybe we want to look at that and say, well, it doesn't take that long to switch the order of integration. Let me see if the other integral works out better. So if I get my drawing going, I'm going to have y equals x, y equals 1, x equals 0, and x equals 1. So again, I end up with a picture that has sort of 2 regions. And the way that I'm going to figure out which one we're talking about, I'm going to put my pen on the lower inside function, and I'm going to move in a straight line until I hit that upper function. And since these were both y on the inside, that means I'm going from there to y equals 1. So currently, this is a vertical cross section. And the area we're looking at is this upper triangle. So if I need to switch that to be horizontal cross sections, then when I switch it, my inside limits, my left-hand side is x equals 0. My right-hand side is x equals y. And this is going from 0 to 1 in the y direction.
how did you get the red cross section? In the middle of one?
Yeah, so I'm going to start and I'm going to put my pen on the function that's on the inside bottom, just like basically in the middle somewhere, and then move in a straight line until I hit the upper function, whatever is up there. So this time what was up there is y equals 1, so I had to move straight up. In the other example, dx was my inside, so when I moved in a straight line to hit x equals 1, that meant I had to go to the right.
Something you said, how do we do this? Respect to x respect to y? Should we see it from here?
Like, how do I know what it is originally? So if dy is on the inside, that means that I have a vertical cross section. If dx is on the inside, it means I have a horizontal cross section. Oh, I got my colors mixed. Let me not do that, because then the colors don't match my picture. Yee. Okay, sorry. This inside function. I got my orientation right. I just want my colors to match the picture. Sorry about that. The other way you can think about it is that the outside integral is the 19b integral. So the outside integral always has to be the one that's got numbers. And what the outside integral is has to match what your 19b integral would have been.